Hi everyone, I'm Kedasha and welcome to Open Source Friday. Super excited for today's episode. We have Akash here from FlashX. I believe it's a simulation software which simulates physical phenomena. I'm looking forward to talking to him about what that even means and how the project works. Hello, welcome to the stream. Thank you so much for being here. Please let me know where you're joining from. And if this is your first time joining, hi, IRT, I'm Kedasha, super happy for you all to be here. So I know we have like a packed episode filled with information. So I'm just gonna bring Akash on the stage. Hi, Akash.
Hello, good morning.
Yeah, nice to see you. So Akash and I know each other in real life, IRL. We met sometime last year in Chicago, and he's always been so passionate about his project. So I was just like, you have to come on the show, and finally we're here. How are you this morning?
I'm good. Yeah, it's cloudy in Chicago, but it's nice. Yeah.
Yeah, I'm joining from Seattle today, and yeah, it's like cloudy, rainy, murky, all that stuff. So let's get right into it, right? So like, tell us about Akash. Who are you, and what do you do?
So I I work at Argonne National Laboratory. It's a Department of Energy National Lab near Chicago. And I did my PhD in mechanical and aerospace engineering, but I sort of like gravitated towards computer science. So I work on mechanical engineering problems from a computer science perspective, which involves looking at developing models to study different problems like how engines work or how cooling systems work in different thermal engineering components or nuclear energy systems, and solving those equations and finding out how to accelerate them using CPUs, GPUs, supercomputers. So that's what I do. Yeah.
Wow, those
Yeah.
those are a lot of words that I've never heard strung together like in my own little world. So a
Yeah.
computer scientist that operates, or like a mechanical engineer that operates from the perspective of a computer scientist,
Yes.
that is
Yes.
such a niche and specific area of this industry. Like, how did you even get into that?
Well, it started during my bachelor's when I was hoping to select my major back in India. I was conflicted between mechanical engineering and computer science, but then through like peer pressure and like advice from more experienced people, I chose mechanical engineering and I didn't really enjoy it. But then towards the end of my bachelor's, I found this one subject, one course that was numerical methods. So a lot of what I do has roots in applied mathematics. And then, so if you understand applied mathematics, you just write code for whatever the concept is. And that's what I was gravitated towards. So I decided, okay, I need to pursue this more. I decided to pursue my master's in the United States because there was more opportunity here. And then I ended up doing my PhD as well. So
Wow.
yeah.
Wow, what a very like intense educational journey, to be
Yeah.
honest. It sounds it sounds like you enjoy the work though. So like tell us a bit more about how you got into FlashX and like how FlashX came about. Like what is this project? How did it start? Tell us the story.
So FlashX is the successor of a previous code called Flash, and
Okay.
Flash has been. Just give me a second. My microwave is beeping. Give me 1 minute.
That's okay.
Yeah.
So today, Akash is here to educate us a bit more about what Flash X is. I'm very interested in this topic because like I've never come across a technology like this before, and the fact that it's open source makes it so much better. So yeah, keep
Yeah.
going, Akash.
Yeah. So Flash was developed at University of Chicago 24 years ago. And it was designed to study astrophysics. So like how stars die, like how supernova phenomena happens. So when a star uh, dies or when the star is birthed, a lot of images that you see from James Webber telescope now, those were things that were simulated because astrophysics, you cannot really do any experiments.
Mm.
But the software was designed by very smart and capable computer scientists. So then it sort of became extensible to other fields. So when I started my PhD advisor was involved with this and focusing on extending Flash for engineering applications. So
Mm.
that's how I was introduced to it. I would say like seven years ago, and then that was my gateway towards computer science and software design because the code was designed in such a creative way that I was just gravitated towards, you know, extending it and making it success. So towards the end of my PhD, they were transitioning to a new version, FlashX, which is Flash for Exascale, because when President Barack Obama was in the office, he signed an executive order on accelerating US's capability in high performance computing, and
Uh-huh.
that led to formation of the exascale computing project. And through that project, FlashX was because they were revamping the supercomputer. So the whole idea is that national labs in the US, they sort of host supercomputers. So if you pick any national lab or Department of Defense, they have supercomputers. And those supercomputers are used to solve challenging problems in AI, in machine learning, in simulations that target specific domains.
Okay.
Um, so when you change hardware, you sort of sometimes have to change the software stacks to extract maximum performance. So then Flash was transitioned to FlashX, and that's
Okay.
how I came involved. So it has been a journey from my bachelor's. Yeah,
Gotcha.
yeah.
So just for clarity and just so I understand, so the initial software Flash was created as a simulation software to simulate, I guess, natural phenomena, so like things that happen in nature, and then it was upgraded to Flash X, which is what you work on right now.
Yeah, yeah,
Okay, great. Got it.
yeah,
Okay,
yeah.
so tell us more about the project. Like, how is it funded? And how does the DOE or the Department of Energy
Mm-hmm.
affect how the project is managed and handled?
Well, so usually, like the process in Department of Energy, the way it works is they send out call for proposals. They are called FOAs, um, and principal investigators, such as me or some senior people who are above me, we sort of put together a project that, okay, we already have something in place. How can we extend this further and fit within the scope of this project? So you sort of get funded through these cycles of projects and you
Mm-hmm.
develop your software. And the idea being that you are targeting specific problems that are of interest to Department of Energy, like problems like solving direct air capture or problems like looking at nuclear nuclear energy systems, like how cooling systems work in nuclear energy systems, or looking at sprays in jet turbines to make sure that you are most fuel efficient. So then through those calls, you focus on a specific problem, and then you develop your software to solve that problem. That cycle sort of continues.
Gotcha. Okay, so let's bring it down a little bit. And I know you have a demo and a small presentation just to help us understand a bit
Yes.
more of the impact of your work. So let's get
Yes.
into that aspect of it.
Okay. Yeah. So what we try to call FlashX is an instrument, right? So think of like a microscope or a telescope. It's an instrument. FlashX is sort of an instrument to do science. That's how we sort of view our software. This work that I'm going to present, like what I've done in the last 3 years, has been supported by two different components. One is the exascale computing project, which has been the flagship project that has been funding DOE for last few years. And then my company, my national lab, which is Argonne National Labs, it's internal funding architecture that gave me some money to work on some of the problems. And of course, acknowledging all the indigenous tribes that made Chicago their land. Without their presence, Chicago wouldn't be what it is. So it's acknowledging them as well. I don't do this work in isolation. I have collaborated across the country. I have collaborators from University of California, from Lawrence Berkeley National Lab in California as well. Back in my alma mater, George Washington University, my advisor, Dr. Elias Polaris, some other professors from University of Maryland, and then my current team at Argonne National Laboratory, and my supervisor, Anshu Dubey, who is the leader of our team.
Nice.
So the way scientific workflow works is that you have some theory, you do some experiments, you generate some data. And the other parallel component is that you have some theory, you do simulations, you generate data, right? So you are generating data, and then you do some analysis, machine learning now that we have those capabilities, and you extract some scientific knowledge. And then that scientific knowledge is used to improve the theory, or to write papers, to understand some specific component of a specific problem, right? So that's how it works. And FlashX fits within that component. So I work on all of these components. I work on analysis, machine learning, theory. But today, what FlashX does, what I'm presenting, is just the simulation part. And then there are other software out there as well. OpenFOAM, which is open source. FlashX is open source. There are commercial software like ANSYS and COMSOL that do the same thing. But FlashX has more robust software design, so you can extend it very easily to different domains. Okay. So what does it mean to do simulation? So imagine you are solving this problem where you have a solid sphere that is falling from air to water. So from T1 to T3, let me pull up the laser here. So from T1 to T3, you sort of, this sphere is falling, it is disturbing the surface of air and water, and it creates this, some disturbance on the interface. So we solve, all of these dynamics are solved by these complicated partial differential equation, right? So you solve for a partial differential equation, and you solve it on these points that you see here. So you integrate them over these points over time and space, and you can compute the solution. So the solution that you see, you can get from this equation. And that's basically what FlashX does. It solves these equations on these points, and you can have different resolution based on the size of these points. Yeah. And we can do different type of simulations, right? So we can do flow over a sphere, or flow over some, let's say, flow over a wing geometry, right? So if you have an aircraft wing and you want to see how the wing performs, you can simulate that. You can do liquid jet. So let's say if you have metal casting, you pour liquid metal into a cavity. You can simulate those dynamics, because when you pour liquid metal, you sometimes get air bubbles inside the cavity, and those air bubbles create impurities. So they spend lots of money to remove when they oxidize. So you really want to understand how not to let these air bubbles get in there. So we simulate that to figure out the best possible configuration to do it. There are other problems like simulating plasma, simulating direct air capture, boiling, how boiling works, which is like an important cooling mechanism in a lot of engineering systems. So you have a solid heater and you can simulate how bubbles boil on the surface. And all of this, all of this happens with using different GitHub libraries, right? So FlashX depends on AMRX, and these are all, if you can go to GitHub, you can find all of these under different organizations, right? So AMRX is the backend that FlashX uses. It's like a backend engine for FlashX. And then once you simulate things from FlashX, you can use BoxKit, which is a Python library, to do analysis and machine learning. You can use FlashKit to do visualization using ParaView. And all of these different components are managed using a tool called Job Runner that I developed, which is one of the things that I have been very focusing on for the last couple of years to make sure how these different dependencies can be managed. And that's the demo that I'll be presenting. And that's the demo that is available in the public repository. I would like to note that even though the FlashX repository is private, we have an Apache 2.0 license. So the thing is, so the repository is private. So you have to request, and this is something that DOE requires us to do because they want to track they want to track who gets access to the code. But once you get access to the code, you can do whatever with it. That's the whole principle. And then, of course, all of these simulations, they operate between different languages. So it's not just Python. We use Fortran, which is an old language.
Wow.
We interoperate between Fortran, C++, and Python. And we run all of these simulations on supercomputers. So we run it on different nodes and run it using different hardware, CPU, GPU. And that's essentially what we do. So what I want to talk about, and so one thing is, if you want access to the code and if you want to do replicate the demo that I'm going to show in the next couple of minutes, go to this page, flashx.org, and go to the code, and you can just put in your GitHub handle, or I think you have to send an email to anl.gov, and they will give you access to the repository. So what we typically do, we follow this policy of laboratory notebooks where you can, so for example, a FlashX developer such as myself, we create laboratory notebooks for specific problems, right? To understand, to simulate direct air capture, to simulate microelectronics cooling. And then we share it with collaborators or perform individual experiments. And the idea being that all of these things that I described in the previous slide, they are very complex ecosystems. And if somebody wants to do actual science, they don't really need to go in and figure out how things are designed in order to produce data. If somebody such as myself who has experience with these things gives them more streamlined interface, then they can run their experiments. And that's what this tool does. What we essentially do is we sort of create these simple commands and create this and we follow this directory based inheritance. So think of like your repository and think of the different folders in your repository. What we do is we organize these folders in such a way that there is some meaning to it. For example, if this environment.sh, which is the file that sits at the top level of your folder, can be inherited by subdirectories so that you are sharing the same configuration. And these script files that you see, these are just shell commands that are complicated commands to set up the configuration of the software. But you really don't have to learn all of those things. These things can be encoded in this directory structure, and then you just use these simple commands to set up your simulation.
Okay, so what we're looking at here is the Job Runner, right? It's a custom built software that is used to manage how FlashX is configured and ran to conduct experiments, right?
Exactly.
And so that's essentially what you're showing here. Just for clarification and just so that I'm understanding what's going on. So when it comes to using FlashX, right? So FlashX is for scientific experiments. So how can I use it?
Yes.
in any way? Like, what would be some applicable ways for someone like me or like another developer to use FlashX?
So for example, let's say you want to study wildfire, or you are working. So one of the things that we are working is, let's say you want to understand how specific physical problem works. Let's say wildfires, right? How wildfires propagate in nature.
Mhm.
Ideally, we would like we can create a lab notebook such as like this that we have here, right? That does wildfire simulations, and then you can generate data. And then once you have the data, we can give you all of that infrastructure to extract some meaning out of it, and then um, uh, and then use it to inform, let's say, create models to inform to predict things in uh, for first responders during a wildfire situation.
Oh,
So
so you can use FlashX to simulate a wildfire and I guess measure how quickly first responders, like how much time they have to respond to it before it gets out of control. Am I understanding what you're saying correctly?
yeah. So not exactly that. So you can use, so think of this as FlashX is just part of the component, right? It generates
Mm-hmm.
the data. So let's say there are some limitations on how much you can measure, right? Let's say if you are putting probes out there in nature to measure wildfire or measure weather conditions,
Mm-hmm.
you you can do only so much through measurements. So sometimes you
Mm-hmm.
need more information, and that's where simulations come into picture, where they can generate the data that cannot be measured or is missing to design more robust response systems, right? So FlashX, running simulations to FlashX will not solve wildfire problems or help first responders. What it will help,
Gotcha.
it will give you the data, and then you can use that data to design systems that are more accurate and better informed, because you are generating more data with more fidelity, with more information, because you're producing this data, you are not really measuring it, and you are producing it at a very refined scale. So yeah.
Gotcha. So
Yeah.
FlashX makes the data available for you to measure
Mhm.
X problem that you're trying to like target or solve.
Yeah. And
Gotcha.
wildfires is something that I just gave an example.
Mm-hmm.
What it really depends on, like I said, all of this really depends on where the funding is coming from. Um, and our what we focus on right now is simulating cooling systems for different engineering components.
Mm-hmm.
So if you are, let's say, designing a new uh, thermal reactor, a nuclear reactor, and you want to understand how how cooling system will work in that nuclear reactor, you can simulate those things using FlashX and generate that data, and then you can plug it into some other workflow that can use that data to identify what are the design constraints. So for example, as an engineer, I'm sitting on my desk, and okay, I want to design a new component for this nuclear reactor. I designed that new component for nuclear reactor, but I don't know how it will perform, right? So instead of manufacturing that component and performing measurements, I can just put it in FlashX to simulate it. And then I simulate it, and I can know, okay, what's going on. And then I can improve my design. And then same goes with direct
Nice.
air. Yeah.
Nice. That's really great. I know you have a demo to show us, so I'd love to, hop into the demo aspect of
Yes.
things.
Yeah. So let me know if you want me to increase the font size.
Yes, please.
Yeah. Okay. All right.
Yeah, that looks good.
Okay. So a lot of times you cannot run these simulations on your local machine. So you have to sort
Yeah.
of SSH into a supercomputer. This is my local workstation called Sedona. It is like represents a single node. It has better CPUs. And
Mhm.
what's going on? Uh-oh. All right. So we are in. Okay. So if you get access to the lab notebook, you can see that there is like a nice README. I have provided enough information in the README, so you can go through everything. But essentially, you set up your software stack. So first you do is pip install requirements.txt.
Mhm.
Uh, uh, right, and the requirements file has all the dependencies that you need. and then you can install additional dependencies. Once you do install, you will have job runner, which is the tool that sort of ties everything together. And then you can set up your software stack. So you can do job runner, set up software, AMRX, which is FlashX dependency, software, FlashKit, and software FlashX. So you are essentially setting up necessary software that is required for this experiment, right? So you can just run this command, and these commands are so simple on the command line. But if you look at individual scripts, for example, let's look at AMRX, right? You have to make sure you are configuring AMRX in the appropriate way to make it work with FlashX. So the idea being that we are masking all of these complexities using this simple tool. And then once you set up all of those, you can set up a simulation. You can do job. So rising bubble is a simple simulation of a bubble rising, and I'll show you an animation. But you set up a simulation, and this is compiling the source code of FlashX.
Wow.
Yeah, and then one thing is that typically you cannot run this interactively. You have to use HPC schedulers. So there are schedulers that are installed on systems that you submit. You say that, okay, I want to run this simulation. You submit that job. You say that, okay, I want to run it with 10 processors, and I want to run it for 30 minutes, right? Or 30 hours in this case. I want to run it for 30 hours with 10 processors, right? So it's going to use 10 processors to run the simulation. So I can just do job runner submit, and then it says, okay, and then you can go to the simulation directory, and you can see this is how the output looks like, right? So this is what it is running in the background. It is using 10 processors to run it, and it is computing your velocity pressure. And then I'll show you how the results look. So I've already ran a simulation.
Oh, wow.
So this is, and then you run it with ParaView. So I think I need to open ParaView. Let's see.
What's ParaView?
ParaView is another open source visualization tool. Let me just put it up here so I can show you the way it looks. This is what ParaView looks. Can you see it?
Yes.
Okay. So the idea is that I have this ParaView client running on my local machine, but then I can connect it to the supercomputer that I just ran my simulation on, which is Sedona. And then it connects to this. So it connects to the supercomputer and gives me access to that data. And then I can use, so I can just go there. So this was, where is it? Open source Fridays, simulation, rising bubble. And then I can open this file. So like I said, FlashX is one component, right? So FlashX did the part, it did the simulation. Now you're using another software to visualize it. So you can, so what you see here, let me take you. Okay, so what you see here is a bubble. So the black line is a bubble that you initially place. So you say, okay, I'm starting my simulation by placing this bubble here. The gravity is acting down. And then this is the pressure that forms around the bubble and outside. So you have air in here, you have liquid outside, right? Inside the circle there is air, outside it is liquid. And as you move the simulation, you can see how the pressure changes. And this bubble moves because of gravity, and then it changes shape. So this is like the hello world simple simulation that you can do with FlashX, but you can do more complicated stuff. So you can see it moves through the air, it splits into smaller bubbles because it breaks up. So
so you essentially just did a simulation locally of rising bubbles.
Yes.
Wow. And this can be replicated from the demo repository you provided us with today?
Yes, as long as you have access to FlashX, you need to get access to as long as you get access to FlashX through the FlashX website, you can do this. And this is just a simple problem, right? So we can do more complicated problems that involve these type of liquid gas interfaces. For example, fuel, how sprays work in internal combustion or like gas turbines. When you spray fuel, how what is the spray pattern that looks like, or how boiling works. So then those are the components. Those are the complicated simulations that you can do, and then you can extract data from here, and you can create plug into other workflows.
Wow, that's pretty impressive, Akash. This is very good work. So walk me through the steps step by step. And can you pull up the demo repository just so everyone can see? And then I want like a step-by-step walkthrough
Okay.
of how we can simulate this project on our own locally.
Okay.
Because that's what Open Source Friday is all about, is about like us being able to replicate this and
Okay.
doing it on our own and say, "Ooh, I'm cool too. Look at what I did. I just simulated rising bubbles."
Okay. All right. So let's say you have access to FlashX. That's the only access you need. Everything else is public. Let's say you get access to FlashX.
And sorry, just to clarify, FlashX is open source. It's just it's managed and it's funded, I guess, and supervised by the Department of Energy. And the Department of Energy requires a list of everyone who has access to FlashX. So in order to get access to FlashX, you would need to submit an email. So you can go to flashx.org, request access to the repository, and you'll be added, no problem, right? And that's how you can get access to it.
Yes. So let's say you get access to FlashX and you clone this repository. First you need to do is pip install requirements, right? And then it will install all the necessary requirements that are required for initial setup. Right? Once you do that, I'm not going to do that because I've already done that.
Yes.
You want to set up your software stack. So first you do job runner setup software AMRX. So when you can just do this and it will just run. So it will tell you, right? It is using config.sh, environment.sh, and setup amrx.sh to build a software stack. You can also use the flag verbose. So it just shows you the shell output of like how it is compiling a library, which is less cool, I suppose.
That's okay.
But okay, so it'll take some time. So this is just setting up the first part of the piece, which is the backend for FlashX, which is AMRX.
AMRX.
Yeah.
And AMRX is included in the requirements.txt?
No, requirements.txt only contains the command line tools that you need to set up, but AMRX is included in software because it requires, you cannot just install it using pip. You have to sort of clone the repo and provide it with proper configuration options that are fine-tuned to FlashX. Right?
Okay.
Then you do job runner, setup software FlashX, job runner, setup software FlashKit. And FlashKit is the software to do visualization. One thing to note here is when you do pip install everything, you may have to update your path. So if you do, for example, job runner, it is stored in my local home bin. So just make sure wherever you do pip install, you need to locate this executable and put the path where this executable is, or in your path variable. So if you do echo dollar path, I have that in my path here already. Right. Okay. So let's say you set up your software stack. Everything is done. You have done all of this is in the README. So I have structured the README so you can follow along. Now we have to set up a simulation. So if you go to the simulation folder, you see different simulation. There is rising bubble, there is flow boiling, there is some instability simulation. And this is the most, so this is the simplest. So you can do different complexities of simulations using just this one executable. I think maybe in the chat, you might, okay, I'm just gonna say, because in chat, people are reporting that they are directly going to the repository.
It's okay. I'll
Yeah.
I'll reiterate it again.
Okay.
Let's keep going.
Okay. All right. So then the next thing you want to do is set up your simulation. So you can do job runner, setup, simulation, rising bubble, right? And it will compile the simulation. If you get stuck or if you get failure anywhere, you can just do setup help and it will tell you what you can do. Usually you can use verbose flag to print out anything. And of course, if you get any issues, you can comment on create an issue on the repository page, and I'm more than happy to help anyone set up. So once you set up the simulation, one thing is that I run this using my scheduler. So what I'm going to do is I'm going to commit the changes that I do right now so that you can run it interactively. So we are just going to use simply bash, right? And within the simulation rising bubble, I'm just going to run it using one processor. Okay, so now you do job runner, submit, simulation rising bubble, verbose. And then you can see that you're running the simulation. So the steps are, first step number 1 is pip install our requirements. That's step number 1. Step number 2 is job runner setup software AMRX. Step number 3, job runner setup software FlashX. Step number 4, job runner setup software FlashKit. Step number 5, job runner setup simulation rising bubble. And then final step is job runner submit simulation rising bubble. And when you do that, it will run the simulation. And you can see all the data here, right? And then once you have this data, you can just do FlashKit. You can go into this directory and you can do FlashKit create XDMF auto, and it will create an XDMF file. And then you can install ParaView on your machine and visualize these files. So then what you do is you go to ParaView, which I have here, and in ParaView you load this file. So let me go back to the process. So you can load this file as an XDMF reader, and you can just look at surface, for example, here. And you can see like the pressure and the velocity. And so this is velocity in this Y direction, and this is the velocity in X direction, right? So ParaView gives you, so you can see all these pixels, right? So each pixel represents a cell, a point where you are solving the solution. So then you have to add filters to ParaView. I can put this filter in the repository as well. And then you just add this filter, and it just, what it does, it creates it does some interpolation to make it look nicer, right? So if you don't have the filter, it looks like this. Let's see, right? It looks like a little bit pixelated, but when you add the filter, it looks smoother. So it's just that, yeah. But
and the filter also allows us to clearly see like the bubbles and like the rising.
Yeah. So I'll add the filter in the repository as well. But if you go to let me go to the job runner repository and just give you, it's like all of these instructions are clearly defined in here. So you can go through it and everything. And if somebody is facing any issues to replicate this, just file an issue. One quick note about FlashX: you have to go to flashx.org, and then you go to code, and you go to source, and then it says the source code is hosted at this. It is distributed up under. So you have to email anl.gov with your GitHub ID, and once you do
Yes.
that, they'll give you access.
Yes, so the code is open source, but because of Department of Energy's requirements, you need to request access to the open source code so they can keep track of who has accessed the software. Essentially, is what's going on. Because
Yeah.
I presume like a simulation software can be used to, do malicious things. Like plan or simulate, how to do malicious activities. So it makes sense why the Department of Energy wants to keep track of who is using the software.
Yeah, and you don't have to be American to use it. You don't have to be American to use it. It's free. I mean, this is just like a we are trying to streamline this process. Let's just say,
Yes.
because we don't really have control. I mean, we want people to use it and use it for different applications. So
Yes.
yeah.
And the best way to get to use it is to just open it fully so anyone can use it. That's going to be like one of the best ways to get people to use it. But yeah, if you want to use the repository, get access to it, definitely, go and request access to it from FlashX site. If you have any questions, drop them in the comments below to let me know. But this has been wonderful, Akash. It's so nice to see all the work that you've been doing. So like, what type of organizations do you know are using FlashX right now?
Mostly universities. I have university collaborators. So there are university collaborators that are using FlashX data to train neural networks.
Wow.
To do physics related stuff. So the idea being that you're going to use this data to train neural networks, and once you have a trained neural network, you can just use it as a way to predict things without running. Simulations are expensive, right? If you want to,
Yes.
like if I'm running like actual 3-dimensional production simulation, it takes around 5 days on a supercomputer. So
Wow.
so if you want to like iterate through different designs really fast, neural network, if you have a trained neural network, that can accelerate that process where you can bypass the simulation. It is being used by my collaborators at George Washington University to study metal casting, to study like one of my collaborators who just graduated, Elizabeth Gregorio. She was studying using FlashX to study how Olympic divers don't retain any cavity when they jump. So she's a swimmer, and that was her PhD project.
Wow.
And so like why they don't retain a lot of cavity, or why don't they create large cavities when they jump? What is the configuration they use? Because they get more points if they don't have any cavity when they jump.
Interesting.
Yeah.
So like how, keep going.
Yeah. So I mean, the possibilities are endless. Wherever you have, let's say, interaction of liquid, gas, and solid, and heat transfer and chemical reactions, you can do FlashX. I'm currently using FlashX to study direct air capture of CO2. So
What?
yeah.
Why would you want to study the direct capture of CO2?
Well, right now, DOE is pretty interested in decarbonization. So we want to, like, we just want to find out all the avenues that are possible to address climate change. Um, and direct air capture is one of the avenues that is being touted as, because once you have a lot of CO2 in the air, how are you going to remove it? The what was I going to say? Uh, right now, the technology requires development of new materials, but then testing those new materials and putting it out there in production environment. So imagine, like, what I imagine in my head is warehouse size plants in cities that are just removing CO2 out of air, and
Wow.
simulating that through FlashX to examine its feasibility. So,
Nice. That is very cool, very important stuff. We have a question here in the comments. Is there any simulation available to analyze server scalability using the data that we have?
I'm
question.
Yeah. So what kind of server scalability are you?
Yeah. Can you narrow down the question a bit more, Vivek? Just so we have some more context. But this has been awesome, Akash. So my other question to you is, how can the open source community, help FlashX or accelerate the work?
So one of the things is hardware architectures are ever evolving. Software architectures are ever evolving. So we need engagement of, first of all, we need engagement for domain scientists who, a lot of times what happens in universities, especially in engineering component, is different PIs, principal investigators, they develop their software in closed ecosystem, right? So they are introducing new algorithms and new techniques to solve complicated engineering problems, but then they are not able to scale. So they can do a very simple problem like this rising bubble problem, but then you want to take that problem and apply it to more broader production problem. And you need scalability and you need performance, but they cannot get to that performance because they are operating as domain scientists who just know how to develop algorithms. They really don't know how to accelerate those algorithms. So when you engage with open source community, what you get is you have computer scientists who are experts in hardware architectures. You have computer scientists who are experts in high performance computing, and they all come together to develop this infrastructure. And then so domain scientists can leverage it. So everybody benefits, and you sort of accelerate these simulation tools to do more challenging problems. And that's the
Nice.
beauty of it. And
So it's
going back,
essentially you want us to use the tool. Is that
yeah,
what
use it.
you're saying?
Yeah, if you are, I feel like if you are a domain engineer, or if you're a computer science engineer, and if you can see how you can contribute to it in a meaningful way, like if you're interested in working with supercomputers, come in. And I think the best way to do it is just like engage with the FlashX team on GitHub. You can file an issue. We have a lot of dedicated people who just are there to, we want to teach people how to use it. We want to help people. I think education and outreach is one of our core principles at DOE. So if you just are curious and ask questions, we are more than happy to show you the ropes. And going back to Vivek's question, yeah, the cloud computing, that is one component that we have been focusing on. We have explored with containers with FlashX. So you can technically build a container using FlashX. There is a tutorial. Let me just point it out. But I think even if you're using containers, what we have found is that it's best to use it on a high performance computing system. So not really have tested much on, not really have tested it on, let's say, Amazon AWS, which is something that I would like to do, but we have done containerization a little bit. Hold on, let me just. Yeah, so if you go to this FlashX/workflows, I think that's one open. Yeah, it's nascent work, but we'll get there. Yeah, containerization is a bit nascent, but we'll get there.
Nice. Okay.
Yeah.
So thank you so much, Akash, for coming on today. This is all the time we have. This is awesome. This is a really, 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 really interesting project, and I'm so grateful that you had the chance to create an Open Source Friday demo for us, so we can try and attempt to, use the tool on our local machines. Thank you, everyone, for joining. Any last words before we end the stream, Akash?
I would like to say that it is very difficult to digest a lot of complexities in one session. So I hope that you understood the concept of what we do in our team. And if you are very interested in it, we are very happy to help. We want people to be involved, and we want to make it easier for people to follow our workflows. So feel free to file issues on GitHub. That's how we communicate. And we are happy to, yeah.
Nice. And with that, we're out. Thank you so much, everyone, for joining. and I will see you on the next one.
Thank you.